Guess we'll start. Hopefully, more people will join. If not, that's fine as well. So, Govind, is it? Okay.
Only
One student.
rooms are left.
It's too much for one student. Okay. I'm happy to keep waiting while this is going on. Maybe somebody will join. So I'm happy to go uh, wait while somebody joins, and then if somebody joins, I can start talking.
Sure, ma'am. I don't
Right?
know why nobody joined.
It's okay. But usually you said only a few people show up, right?
Yeah, this time not many people are coming to the session. So Govind
Hmm.
is the only one who
Ah,
has been
okay.
coming. He joined back. Yeah.
Okay.
Yeah, sorry.
That's okay.
Uh, Good evening. Actually, I'm driving. Actually, I submitted 4 questions, madam. I think the first
Okay.
question I had was in the accept reject method.
Hmm.
What is the primary reason that we assume that it is very difficult to draw from the target distribution? So we kind of assume that okay, this method can be used whenever it is difficult to draw from target distribution, and we just go ahead with the proposal distribution, right? What is the primary reason? Why is it so difficult to draw samples from the target distribution?
So let me just ask for a quick clarification. Are you talking
Yeah.
about the discrete setup case or the continuous setup case?
No, any method, any situation. I don't
Ah,
know whether if it is a different. No, in the case of discrete, you mentioned that the if conditions could be very compute intensive, and the algorithm can take long, right?
mm-hmm, mm-hmm.
Whereas no, is it the same reasoning for
No.
the continuous also? Why is
No,
it
no. So,
in general? Why is it difficult to actually draw from the target distribution?
so first, first thing is to just understand that we are doing the accept reject to draw from the target distribution, right? So maybe your question is why can't we use inverse transform to draw from the target distribution? Is that the question?
No, no. My question is, yeah, we want to draw from the target distribution.
Yes.
The premise that we are going for a proposal distribution because uh, it is not feasible to draw from the target distribution easily, right?
Yes, and that is the purpose of accept reject algorithm is to draw from the target distribution itself, right? That is the
Correct,
purpose. Yes.
correct. And
Now
we are not.
the
Yeah,
go on.
please. So that is a purpose, but the motivation to draw from a target distribution,
Hmm.
uh, the motivation to draw from a proposal distribution instead of target distribution is uh, it is difficult to draw from the target distribution, isn't it? It is easier to
Yes.
draw from the proposal distribution.
Yes, yes, exactly. So I'll give you an example, right? So do you have access to seeing my screen right now?
Yeah, yeah.
I mean, on while
I
traveling? Okay,
yeah, yeah, yes.
okay, okay. So then I'll write down. So, so I'll talk about the discrete case later, but in the continuous case, let's consider the example of, I mean, we did this, I think, in the notes of considering that the target is a Gaussian target, right?
Mm-hmm,
A standard normal 0, 1. Okay.
mm-hmm,
Now, there is the by the result that we know to be true, that if I take uniform draw between uniform 0, 1, and if I set F inverse U, if I look at this random quantity F inverse U, where F is the CDF of the distribution, right? Of my desired distribution from which I want draws. Okay. Then I know that this quantity, this itself follows the distribution F. Okay. This is what the inverse transform method says. So from that premise, we know that if I can just draw this uniform and apply F inverse to this uniform, I will get a draw from F. So in that sense, we shouldn't need any other algorithm to do this, right? To draw a sample from F. But for the case of, for example, the Gaussian, for this case, f of x, which is the CDF function of a Gaussian, is integral of minus infinity to x e to the power, 1 by square root 2 pi e to the power minus x square by 2 dx, right? Sorry, I should use, I should be careful. I want to use dt here, right? Because I already have x in the integrand, so 2 dt. Yes? This is what the CDF is. Now the problem is, over here, the problem comes in this, for example, Gaussian case, that I can't solve this integral. It is one of the common integrals that we know we can't solve. So if I can't solve this, sorry?
The inverse function cannot be interpretable.
Exactly. There's two problems actually. The actual function is not analytically available, and the inverse I can't analytically obtain. Sometimes my function is available, but I don't have the analytical inverse, that I can't actually write down the inverse very easily. Okay?
Right, okay.
That is one problem. Here the problem is f itself I don't have. Okay? So if I don't have it, then I can't find the inverse. Now, if I look at accept reject, I can think of consider proposal Cauchy, right? Standard Cauchy. But now Cauchy, with I say CDF, I will denote the CDF of Cauchy as G. But now Cauchy, I know G of X, we found G of X to be, I think, what was it? Tan inverse, I think, what is this? Tan inverse 1 by pi tan inverse x plus half or minus half, something like this. Okay?
Right, yeah.
Something like this. And then it was known that for this particular case, G inverse U is going to be tan of pi times U plus half. Right? Something like that. Maybe I'm confusing. Maybe it should be like this.
It's okay. I got
Yeah,
so because f inverse is not obtainable, so we are actually going through this route test. In case of continuous. Okay.
Yeah, exactly. So I often will not have f inverse available. So the Gaussian is one example. Another example is gamma, right? So, and another example is gamma. I don't have the CDF available of the gamma distribution, so I need to resort to some sort of accept reject or some other algorithm. Basically, it may not be accept reject. We are just discussing accept reject as a potential algorithm that can work in many cases. But when accept reject cannot work or is not efficient, we will also do a couple of other algorithms.
Okay. So whenever f inverse is obtainable, so we can just go by that drawing from the uniform and seeing if it is less than, and we can go ahead and draw, right? Okay.
Yeah. Without a doubt, that will be the cheapest, most effective way of sampling. Okay. When that's possible, we should always just do that. That will be easiest, most effective, not difficult. But when we can't do that, then only we will resort to the other algorithms.
Okay, right.
Okay.
And the second question I had was about the composing distributions.
Compositions.
The compositions. Is there any case that that we use compositions as a proposal distribution? If so, one of the scenarios it occurred to me is like, whenever the support is supposed to be a superset of the proposal of the target distribution. So that was the condition that you mentioned, that for the proposal distribution, the support should be a superset of the target distribution. Then only we can use it as a proposal distribution. So is there any scenario that we use this composing distributions just because we do not have a suitable proposal distribution, we come up with some kind of a composition and use it as a proposal in some method somewhere? Is there any scenario?
Yeah, absolutely. So I'll give you another example. So for example, we will get to gamma distribution, alpha beta. Now when we'll get to slightly more analysis and accept reject, I'm not sure if you've gotten, we've done that in the week already. But if I look at gamma, alpha, beta, when alpha is less than 1. Okay? So the issue is when alpha is less than 1, then gamma starts looking something like, something like this. So this is f of x, okay, and this is x. This is the density of gamma when alpha is less than 1. Now the issue, as you can see, is that what we are going to have is over here, as x goes to 0, it actually becomes an asymptote. Okay, it will keep going closer and closer beyond because it becomes an asymptote. Okay, so now I know to implement accept reject, I need proposal G, then proposal density G, so that soup of f of x by g of x is finite over my support, which in this case is x greater than 0. Yes.
Yeah.
Now the issue is that because because f of x is diverging, right? I'm actually going to require in order to get f by g to be something that definitely goes, that remains unbounded, that doesn't diverge to infinity. I will need g of x so that it is always larger than f of x, right? It is like this,
Mhm.
at least near 0. Only then will the new denominator be somewhat larger. Yes.
Mhm.
Now, if I construct it like that, remember this G and F both have to be densities, so they have to both integrate to 1. So then that means I need to have this go on the other side to 0, right? So it has to be larger on this side and smaller on this side because they have to integrate, both have to integrate to 1. So if it's larger here, it must be lower here. Yes?
Yeah, correct.
Correct. So that trade-off has to come. So that means if I choose a g of x so that it's better here, on this side of the tail, I will get f by g to go to infinity.
Mm.
Yeah. And on this side of the tail, I may get f by g to go to infinity if I do it the opposite way. So what
Okay.
one does is that between 0 and 1, so between 0 and 1, you can define a beta proposal that actually looks like this. Okay, oops. So book beta proposal that actually looks like this. Okay, and then you can define another distribution. It doesn't need to have a continuous PDF anymore. By mixture, you can say, okay, it's by 0, 1 like this, and maybe an exponential or maybe something similar to that on from 1 to, sorry, 1 to infinity.
Mhm.
Okay.
Okay.
Right? And obviously the beta only is defined in this support, but the exponential might also be defined in this support, but we're not going to consider that part of the support. So with probability half, the proposal will pick up from here, and with probability half, the proposal will pick up from here. So it will have a tail structure for both.
Oh, I see. Okay.
So that is absolutely right. It can be useful to define proposal distributions using compositions so that you can actually get a specific behavior in different parts of the space.
Okay. So are there any specific techniques to do this composition, or is it
No.
like a trial and error thing?
So the specific techniques for accept reject to do the composition is just to understand what your behavior in the two tails looks like. See, what happens is anywhere we can actually see the function. If I can, when I draw the function, I'm going to draw it in R or on paper. You're always drawing it on some finite or bounded support, right? You can't draw till infinity.
Correct.
Right? Or you can't go infinitesimally close to 0. You're
Correct.
always going to draw it in a bounded way. So any points that I've drawn it, any proposal I draw, for that f by g, for all the points I have drawn is finite. Because I can see it. F by g may be large, but it will be finite.
Right.
So it will be only the points I cannot draw, which is at infinity and very close to 0 in this case, where I don't know the behavior.
Right.
Right. So those are the places where this is going to be effective. Right? So one has to then, when you're trying to devise the composition method, you're going to have to look at what the tail behavior is in this side, choose a proposal that works well with that tail behavior, that for which G has a heavier tail in that direction. And on this direction, choose a proposal where G has a heavier tail in that direction, and then compose those two.
Okay. So this leads to a generic question. So whenever like we are in statistics, we have this problem of fitting a distribution to a situation, right?
Mm-hmm.
So is it a practice to do this composition even in those scenarios also?
Yes. So a composition. So I just want to clarify one thing before I resume. Obviously, we are currently we are talking about sampling from distribution.
Sampling, exactly.
Yeah.
Right.
But now the question you're asking is about fitting to distribution.
Fitting to distribution, exactly.
So that's exactly correct. So when we get to a couple of weeks fast forward, we will talk about the EM algorithm. And when we talk about the EM algorithm, a prime example would be to try and fit a mixture of normals, a mixture of Gaussians to some observed data. Okay. So we will get to that. So for that, we need to understand what a mixture distribution is, a composition distribution is. And so we are sort of building the framework right now so that we understand how these distributions work.
Yeah, but in this scenario, the composition is piecemeal, isn't it? Like in this scenario, whatever you just drew and explained, this composition is a piecemeal composition. Like in a specific range of support, we have some distribution. In other pieces of other ranges of support, we have other distribution, right? So these kind of fitting, like you said in the class also, you said the COVID example where at the zero it is like zero inflation is required and you are using this kind of fitting, right? So there from the COVID example, I kind of drew a conclusion that okay, you saw data and you drew the data and the frequency distribution of data is in certain format, and to that you're trying to fit a distribution. So there you had a choice of option, requirement of inflating on zero, so you came up with that kind of a piecemeal setup. And similar thing is, but here the context is that you want to use it for you are using it as a proposal distribution.
But the idea is that the mixture distributions and composition of distributions exist to give us this type of flexibility as and when we require it. Okay. In the COVID example, what happened is, yes, one can think of it as two things. One can look at the data and then think, oh, I need a distribution like this, right? But even philosophically, even before you look at the data, one must sometimes decide what is the philosophy with which I'm going to analyze this data, right? And even then, one knows how these examples are going to come about. One knows that there will be some hours where there will be very little zero positives, right? So you know the philosophy already. So instead of just blindly fitting that, okay, let me use this distribution because it looks something like it, one also has to go back to the philosophy and say, philosophically, I have count data, so Poisson makes sense because that is typical for count data. But I know that there will be some positive mass at zero that needs to be accounted for, that is over and above just regular Poisson.
Right.
Okay. So that brings in that philosophy. Right. Okay. So, for example, I mean, there is another example one can think of, which is insurance claims. Right. So, insurance claims typically for a particular for most users in a calendar year of, let's say, car insurance will not claim any insurance because no accidents happened.
Right.
Right. So a claim of insurance per user for most users will be zero.
Right.
But then when an insurance is claimed, it will be 5,000, 10,000 rupees, right? So it will have some continuous distribution on the positives.
Right.
So some gamma or something like that. But there will actually be a point mass, right? Like something like this, that if I were to draw a density, now we have to be careful because now this is a mixture of discrete and continuous. Right? Because usually I don't have positive mass on any number for a continuous variable.
Yeah.
But now at zero, I will say that I put let's say 50% of the mass. 50% of the population has no claims to make.
Mm.
And then I will do a a PDF, which is, let's say, the gamma, right? So other half of the mass is given to this gamma. So this is what like the density function, quote unquote, will look like. And here I know the philosophy with which I'm coming. I know that there will be a mass at 0. So I have to pivot to a distribution like this.
Okay.
Okay.
So yeah. So so there are in general, like for example, in the linear models, in the linear models and all, we'll broadly make an assumption that everything is Gaussian, independent, and all those assumptions are there, right? Are there any situations where, because we are fitting these kind of piecemeal things, those assumptions are broken and we have to use a different method to solve the problem of
So
regression?
right. So in a lot of statistical models, especially for example the linear models, one has to ask you have to ask yourself, okay, great, I have assumed Gaussian structure. Okay, I've assumed normal structure, but let us ask ourselves, where is that normality being actually used? At what point? Yeah, I've assumed it. Maybe I've assumed it for convenience, and maybe I'm actually using it. But at what point am I using it? So let's talk about linear regression. Okay. In linear regression, I assume the errors are IID normal. Yes. But the estimator for the regression coefficient I have, this beta hat, which is X transpose X inverse X transpose Y, right?
Yeah.
This is an OLS estimator.
Right.
That no matter what error you assume, is distribution you assume for the errors, the OLS estimator will always be this.
Right.
Because it's least squares estimator, right? It was
Right.
obtained by minimizing y minus x beta,
right,
over all possible vectors beta. Yes. And this is always going to be, for least squares, this is what we're minimizing. So it doesn't matter what epsilon follows.
Right.
So then the question is, where did we use the distribution of epsilon? Where did we use the Gaussian assumption? Can you recall?
No, I think it was about the good estimator, right? Blue estimator. I think the theorems
the best linear unbiased estimator, all of that will assume Gaussian error. Okay. Yes. Right. But particularly within this structure, the reason is that once you start getting into a null hypothesis of whether beta is equal to 0, which is there the regression line actually useful or not, then I have to start thinking about beta hat's distribution.
Correct. Yeah. Right.
And there I will use Gaussianity, right?
Right.
So, but the reason I'm bringing it up is typically, not always, or we can't generalize, but typically we are going to use errors and distribution assumptions only when we get to inference.
Oh,
okay. Not often, not when we are doing estimation. Now, this is not true. It is not always true. Even in our course, we will get to doing take logistic regression as an example to do something. There, the distribution will be important. Okay, but at least in the linear models framework, this typically inference is where we require the assumption.
Got it.
Okay.
Yeah. All right. Okay. Yeah. Thank you very much. I think that's all I had. I think around 3-4 minutes now.
Thank you. Thanks, Govind. Do we want to keep on just in case anybody shows up, Nikita?
Ma'am, I think it's better to close because it's already been half an hour.
If no one is there, can I ask one more question, Professor?
Yeah, of course. Please go ahead.
Yeah. So we are I think whatever we are discussing in the course is basically the fundamental tools on which, and as you said, the techniques are built on. So, are they, in what way the current the machine learning and the whatever advances are there? Are there any direct relations, or where I mean these techniques are directly used, or some kind of in order to build a mind map, right? From
Yeah.
where we have and what we are doing in the real world in terms of whatever the
Right.
latest techniques that are available.
Yeah.
Can you please help
So
draw that mind map?
yeah, sure. So the first 2 weeks, maybe 2 to 3 weeks, we are reviewing sampling from different distributions, and
Mhm.
a direct impact is maybe unlikely, mainly because a lot of the functions that we use to sample from things are already coded.
Right.
Okay.
Right.
However, there is a whole sphere of probabilistic inference or generative modeling in
Mhm.
machine learning. In statistics, we call it Bayesian statistics, which
Oh,
which require a lot of sampling intensive paradigms, which are
mm.
basically this, right? We have to learn how to sample from distributions in
No.
generative modeling or Bayesian statistics. And
So,
that's where some of these tools, now these tools are more fundamental and may not very directly apply, but they're all algorithms are built on these tools that we are discussing.
right.
Okay.
There are a little higher level of abstractions built on
Yes.
these, which we can eventually use them.
Yes,
Okay.
exactly. But if we don't cover this, then it's very difficult to understand other sampling algorithms.
Got it.
But then
All right.
further, when we go into starting, and after this, we'll go into importance sampling, and then we'll go into optimization. Now, almost everything we cover in optimization will make the building blocks of all machine learning algorithms, because modern machine learning at the end of the day is all about optimization.
Right.
Where
Right.
where interesting things happen is when we learn, when we understand what do we actually want to optimize. That's where the statistics and machine learning happens. But to actually implement our intentions and implement our algorithms, one has to do optimization, and that is where we are going for, maybe the 60% of the course. Okay.
Right. In the reinforcement learning
Mhm.
subject, so I think there was I heard about something called Thompson sampling,
Yeah.
and so are there any relations between what we're going to study and that?
So we will not get to the concept of Thompson sampling, partly because one also needs to understand something on Markov processes
Oh,
to get to those topics. But
okay.
I will say Thompson sampling and other sampling methodologies are inherently built on sampling strategies like these.
Okay. Okay.
Okay. So yeah, we can't necessarily make that jump, because otherwise this whole course will be about sampling. And we would want to do it about all sorts of computation that are involved in modern statistics.
Okay. All right. Okay. Now,
Okay.
I was just telling Nikita, just
Hmm.
to draw these mind maps and probably future learning paths for
Yeah.
our group, right? Probably if you can provide those resources and guidance, maybe if it is if you think it is relevant to us, you may do so. That
Yeah,
was
yeah. No, I think that's a good idea. I think this is something we've discussed in the past as well. It's slightly. I think utility will be seen fairly soon, and so I feel like after 3 weeks one starts seeing utility.
Hmm.
But maybe it would be so for me that is good enough. But I can understand for most students one would like to see something immediately, and so we'll probably start thinking of like a good toolkit to share to understand where direct utility is.
All right. Yeah. Yeah.
Yeah.
Thank you. Thank you very much.
Yeah, no problem. Okay, so maybe it's fine to close, Nikita.
Yes, ma'am. We can close the session.
Okay, okay.
All right. Yeah. Thank you very much.
Bye bye. Yeah,
Thank
no
you.
problem.
Have a good night. Bye.
Good night. Bye bye.
Good night.